Hello, my students. This is P. Venkateshwarlu, PGT Physics. In previous video, we have already discussed about the stress-strain curve. Okay, so based on the stress-strain curve, we have to define the materials into four types. Okay, see means what are they means ductile materials, brittle materials, malleability and elastomers. Okay, so now we have to discuss about that is the first one, ductile materials. Ductile materials. So in this type of materials, so when we are applying load or stress means the materials will elongate. Okay, and understand. So we are applying force means the material will not breaks, it will elongate, means the length increases. Understand? The examples of these materials iron, copper, aluminium, mercury. Iron, copper, aluminium. Okay, see, we can observe this type of materials graph. This is origin, this is stress, this is strain. We know that O to A proportional to limit, A to B elastic limit, and B to C permanent set. From C to D, here the C to D. Okay, if the value C to D is large, okay, large or more, okay, more, we can say ductile materials. Say in a stress strain curve, we can observe from the C to D, that is when we are applying small stress, the material will enlarge. Okay, beyond that the wire will breaks. Beyond that the wire will breaks, my children. Okay, this type of materials we can say ductile materials. Example iron, copper, aluminum. Okay, because of this ductile property of material, we can made into small thin wires. Understand, my children? Next, brittle. Next one, brittle materials. Next one was brittle. Brittle materials. Okay, see here in this brittle property of brittle materials, which are defined as the material which have small elongation, means there is no elongation. Okay, so after elastic limit, okay, we can apply stress, means the wire or the materials will breaks. Understand? So whenever we are applying load, okay, beyond that elastic limit, what happens? The materials will breaks. Example, glass, cast iron, ceramic. What are the examples? Glass, ceramic, cast iron. Okay, for this type of brittle materials, we can have graph, that is stress and strain curve. We can represent OA is proportional to limit, A to B means we can say that is elastic limit, B to C permanent set. Okay, then after getting C, we can get D, means from the C to D is small. Okay, understand? So after reaching C, the material will get of fracture point or will breaks. Understand? So within elastic limit or permanent set, so the material will not happen anything. So we can apply stress beyond the permanent set, so the materials will break. So example, glass, ceramic, cast iron. So we can apply more force, means it will bear some time. After that the materials will break. Example, glass, ceramic, cast iron. Okay, understand? Next one, malleability. 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 Okay, so this is somewhat different medicine. So here, whenever, so according to this stress strain curve, so always we are applying load. Okay, we can get the strain. So whenever we can, this is purpose based on the elongation. So whenever we are applying force, means compression. Understand? So at the time, so when we can compress a body, okay, we can remove this this deforming force. The material will regain its original shape and size. Okay, beyond crushing point. Okay, so means crushing point means, my children, crushing point. Okay, so whenever we are applying deforming force, the material will not regain its original shape and size after getting crushing point. Okay, understand? So beyond crushing point, the material will not regain its original shape and size after removal of deforming force. Okay, so for this examples, what we can say? Yes, gold, silver example. What now? Gold, silver. Means AU and AC. Okay, understand? So for this graph, we can observe that. So here we can observe that stress and strain. We can get this point O2 A dash and B dash. Okay, so whenever a body reaches to B dash, or we can say that is a permanent set, or beyond B dash we can say crushing point. Okay, so whenever we can apply this deforming force while compressing, okay, the material will not regain its original shape and size. Okay, this type of materials we can say malleability material. So by this is very important properties of this type of gold, silver. So by hammering and by rolling, we can make it thin sheets or thin wires. Okay, understand, my student? Which is very important one. Okay, so here A dash we can say elastic limit, B dash is we can say crushing point. Understand, my children? So after reaching the crushing point, the material will not regain its original shape and size. Okay, understand? Understand, my children? Next, elastomers, my children. Next one, elastomers. Elastomers. Okay, see here, elastomers means which having large elongation. So the graph between stress and strain curve like this. Okay, so means elastic materials or elastomers, which is defined as a material which having large elongation means with less amount of stress we can observe more strain. Okay, a material which have more strain, this type of materials we can say elastomers. Okay, so whenever we can apply the this type of stress means we can observe more strain. Okay, so this type of materials we can say elastomers. So large value of strain, we can say this type of materials large value of strain. Understand? So we can say example, best example for this elastomer is rubber. Understand, my children? Understand? So this type of ductile materials and brittle materials, malleability and elastomers. Okay. So coming to next content, my children. Coming to next content, elastic modulus. Elastic modulus. Okay, so after before going to discuss about this strain and stress, we have already discussed about this elastic modulus. Okay, so what is the definition of elastic modulus? Within the elastic limit, the stress is directly proportional to strain. Okay, understand? Yes, within the elastic limit, stress is directly proportional to strain. So we can say Hooke's law. Okay, this stress is equal to E into strain. Okay, then E is equal to stress by strain. Understand? So this E is equal to elastic modulus. Elastic modulus means this SI units strain having no units, because it is the ratio of same quantity. So that's why SI units stress pascals by strain no units. Pascal means Newton meter power minus 2. Newton meter power minus 2. Understand, my children? So this is about elastic modulus. Understand? So what is elastic modulus? The ratio of stress by strain is called elastic modulus. So here elastic modulus depends. First one, nature of the material. Nature of the materials. And second one, dimensions. Means what is dimensions? Length, area and volume. Okay, so elastic modulus depends upon 2 points: nature of the material, so which made of iron, copper, glass. Okay, different materials having different elastic modulus value. And second one, dimensions. Okay, length, area, volume. Okay, it is depending upon these factors. And we know that main important one, elastic modulus having same dimension formula of pressure and stress. Understand? So elastic modulus having same dimensions of pressure and stress. So because of this having same SI units and same dimension formula, but somewhat definition is different. Understand, my children? So coming to Young's modulus, next content, Young's modulus. Young's modulus. My children, so next we are discussing about Young's modulus. It is denoted Y. Okay, so we know that elastic modulus means stress by strain. So coming to this Young's modulus, so before going to this, we have to take one wire or one material based on the length. So we have to apply force on the material. Okay, the material will elongate. Okay, so when force means stress is applying on the material, we can get the length of the material will increases. So based on that, we have to find stress and strain. Okay, already we can recall it longitudinal stress and longitudinal strain. So this this Young's modulus, it is denoted by which is equal to longitudinal stress divided by longitudinal strain. Okay, so the Young's modulus, which is defined as longitudinal stress to the longitudinal strain. Okay, so we can say that is tensile or compressing stress divided by longitudinal strain. Means, so here longitudinal stress is not always the force is applied, the material will elongate. Okay, sometimes the material will have to compress. Okay, so that's why you can say tensile or compressing stress or longitudinal strain. Okay, so this longitudinal or tensile compressing or stress, or this we can say sigma. Longitudinal strain we can say epsilon. So here y is equal to Young's modulus, y is equal to sigma by epsilon. Young's modulus y is equal to sigma by epsilon. So what is the definition of this Young's modulus, my children? The ratio of longitudinal stress divided by longitudinal strain is called Young's modulus. This longitudinal stress, you can also call it tensile or compressing stress. Okay, understand? So which is denoted longitudinal stress, we can denote it sigma. Longitudinal strain, it is denoted epsilon. So y is equal to sigma by epsilon. Okay, so understand my children. Next, coming to its units. Okay, any modulus we can have same units. Okay, understand my children. Y is equal to sigma by epsilon. Okay, sigma means force per unit area. Stress, force acting per unit area is called stress, divided by change in length by original length. Okay, we can denote it F L divided by A into delta L, my children. Okay, understand, my children? So based on this Young's modulus, how we can find this Young's modulus of any material means, so consider two wires. We are applying force, means some weight is acting on the material. Okay, understand? If mass W is equal to mg increases, means what happens after some time, so we can observe the material will increases its length. Understand? Okay, so the material will increases its length. Okay, if m is more, understand? So initially the length is L. Okay, after that so the length of the material increases by delta L. Okay, this part increases. Understand? By the applied force, W is equal to mg. By the applied force, W is equal to mg. Understand? So in this case, so we have to substitute F is equal to W is equal to mg. F is equal to W is equal to mg. So then Y is equal to mg L divided by delta L into A. Delta L into A. Understand my children? So Y is equal to mass acceleration due to gravity, length, change in length by area. Suppose we have to take all our unity. M is equal to 1 kg, G value 9.8, L is equal to 1 meter, delta L also 1 meter. Okay, A is equal to 1 meter square. 1 meter square. Understand? So 1 meter square. See here we are all these values taken as unity. Okay, understand? So how we can define this means Young's modulus. Young's modulus means Y is equal to everything we have to take unity means not to have to take unit mass. Mass is equal to 1 unit. Okay, understand? See here, finally we can get Y is equal to mg, means Y is equal to this F. Okay, Y is equal to F because L is equal to 1, delta L is equal to 1, A is equal to 1. Mass is 1 unit. So that's why remaining this mg is there. Okay, mg is there. See here, which is defined as, okay, so elastic modulus or coefficient of elastic modulus, Young's modulus we have also, which is defined Young's modulus, which is defined as the amount of force. The amount of force is required to change the length, means to increase or to extend the length of 1 unit of material and 1 unit of cross section area by unit. Okay, my children, once again listen carefully. Young's modulus that is defined as the amount of force required to extend the wire of unit length and unit cross section area by unit amount of length. Okay, means by taking all our unity, Young's modulus, which is also defined as the amount of force which is required to increase the length of the wire and having unit cross section area by 1 unit. Okay, simply the amount of force is required to increase the length of a material by unity. Okay, understand my children? Yes.